I want to start by talking about the symbol processing approaches. And I'm going to take Newell and Simon's approach and their work as really emblematic, but there are, of course, many other researchers who would fit into this category or this school. So these approaches were applied to problems like, can you build a machine that can do proofs in geometry, that can prove theorems in geometry, or a machine that can do proofs in something called symbolic logic? There were programs developed using this approach that could solve calculus problems. For instance, could solve problems in college-level calculus textbooks intended for undergraduates. There were programs that had a high success rate in finding the solutions to word problems. There were programs to play chess, to play checkers, and a kind of problem that we'll look at as an example, which is a sliding number puzzle. I want to just point out a little bit about how the symbol processing approach thought about what computation was, what a thinking machine would be doing, right? What would an intelligent machine have to do? Whatever computers are, we know that they are symbol processors, that they can process symbols and that they do process symbols at some level of their design specification. And we can think about these symbols here at the top of the screen as encoded just in zeros and ones if we want to, because we can have a unique code in zeros and ones that expresses each letter of the alphabet. We can have a unique code to express any 2-digit, 3-digit, 4-digit, and so on number. That's not hard to develop conceptually or mathematically, these kinds of unique codes. And so once we have that, then we know that we're able to basically give instructions to any computer that manipulates symbols of that kind. And we can also put symbols into lists. And we can also put lists of symbols into lists so that it's clear which lists are inside which other lists. And then we can perform transformations on lists. Like we can say, take the second item in the second sublist of the first list and delete that item and insert into the place the symbol taken from the first item in the third list, or something like that. Okay, so any kind of transformation of these lists that can be unambiguously stated, that some instruction can be written to transform the list in some way based on a rule, is something that you can program a computer or a computer program to do. And so the symbol processing approach to building artificially intelligent machines and programs involved just this: stating problems or stating behaviors in terms of transformations of symbol systems. And then the exercise was to write a program that would solve that problem, that would find a solution to the problem, where the solution, again, has to be specified in terms of some string of symbols or a string of symbols that meet some criterion. And you can see how, this technique promises progress with something like programming a computer to play chess, because it's about finding the most effective move given a certain position of the pieces on the board, and all of that can be written in terms of instructions for how to what choice to make or what answer to give in terms of something that can be presented just as a set of symbols, instructions for where to move a chess piece. That can be given unambiguously, and a rule can be given for producing such an answer given a certain configuration of the board. So there's nothing conceptually puzzling about whether or not you can write a program that can do that. The question is, only how to find the program that does the best job of playing chess, or find a program that does a pretty good job of playing chess. How to write that program, right? What will that program actually in its details look like? What will be the specific moves that are recommended given a certain configuration of the board? And of course, how will we as the programmers find those rules? How will we, use whatever computational processes we can imagine or we can invent to discover the best choice, or at least a very good choice of a move, given a certain configuration of the board. Well, so far I've described this approach in a pretty general and general strategies type of way. I'd like to get down into something a bit more concrete, if we can, looking at a particular kind of problem that this approach is well designed to solve, or has a good chance of getting us a solution for. So this is the sliding number puzzle. In this case, it's called an 8 puzzle because there are 8 numbers that have to be ordered in a certain sequence. And the idea here is that the blank space in that initial state configuration of the board, the blank space just represents a place where there isn't a little wooden tile, but all of the other spaces have a wooden tile, and the wooden tiles can be slid around inside the puzzle. So we could, starting from that initial state, slide the 2 down into the 3rd row, or we could slide the 6 over into the 2nd column, or we could slide the 3 over into the 2nd column. And those are really the only 3 moves that we can make starting from the initial state. And each of those moves, of course, will then move the placement, not just of the piece we move, but of the blank space. Now, the first step in approaching this, as is often the first step in applying a simple processing approach to solving some problem, is to represent the problem unambiguously in a way that can be encoded in a computer program. And so we can use our observation that we can always put information about lists and lists of lists into a program, and we can instruct the program or instruct the computer to do transformations on those lists. So we can use that information to decide to express the initial state as a list of lists, basically a list of rows in the 3-row table here. And we can describe the goal state as a list of rows as well. And then we can describe some allowed transformations that would allow us in a stepwise fashion to get from the initial state to the goal state. And we need to express those transformations in terms of transformations of the initial state list. Okay, so what can be done to that list to get us to the goal state? And the idea is we can carry out these transformations as many times as needed, but what we're looking for is the sequence of these transformations that will get us to the goal state. And so the allowed transformations here they basically have to do with swapping the blank space with one of the spaces adjacent to it, and that is expressed in terms of the 2 rules given on the screen here. Now, once we've expressed the problem in this way, we can do what's called a search or an exhaustive search, or is sometimes called building a search tree, to look at all of the possible transformations that can be conducted from the initial state to a subsequent state, and then from each of those subsequent states to a state after that. And so the full diagram that describes all of these possible transformations is called a search tree, because it's like you're searching all possible transformations, right? You're drawing out something that looks like a tree, and that tree explores the total decision space of the program, all the decisions that it could make from the initial state on. Now, this is clearly a very clever idea to, do an exhaustive search across all of the possible transformations that could be made. But the problem is that very quickly the number of possible choices that could be made becomes computationally intractable. In other words, it becomes so large that there is no known program that can run through it and calculate and actually consider actually compute every single possible transformation. With this problem, it could be done. This problem is not computationally intractable for an exhaustive search. With chess, for instance, chess is a computationally intractable problem, and it still is in terms of exhaustive search. And this problem was called by these early AI researchers the combinatorial explosion, because since at every branch point you get a new set of branches, and then at each of those branch points you get a new set of branches, it just this graph grows not just exponentially, but more than exponentially. It grows very, very quickly, and it's that explosion is hard to contain and it's hard to computationally to work through in terms of exhaustive search alone. So what do we do about this problem? The classic answer proposed by the symbol processing approaches was something called heuristics. Basically, what it involves is narrowing down the search space somehow based on some assumed rules. And so an example that's given by Nilsson, which won't actually work very well for this problem, but it's at least a good example of what a heuristic is suppose we adopt the heuristic that we won't take on any paths, we won't even explore any paths that move one of the pieces further away from the position that we want it to be in the final state. And if we adopted that rule, then in this case, that would allow us to just lop off 2 out of the 3 branching paths right from the beginning. And that will cut down our search space for sure. And we can continue, if we continue to employ that, it would certainly cut down our search space. Again, this heuristic might cut down the search space too much, and it might prevent us from finding the solution. But it helps to clarify, I think, how a heuristic can function to narrow down the search space and get us closer to the right answer. For instance, in a chess playing program, you might have a heuristic that queen will never be sacrificed unless within 4 or 5 moves, an equivalently good trade can be secured. That would at least cut down on the number of branching paths that the computer had to consider. And of course, when you couple these heuristics with others, you kind of you pile on a set of different heuristics, then you can really narrow down the search space quite a lot. One particularly interesting and important subset of these heuristics is something called using sub-goals or reasoning backwards. Now, with this problem, it's a little hard to see. I don't think there's really any advantage, computational advantage or efficiency advantage in reasoning backwards rather than forwards. But with problems where the search space is the initial search space is very large, then sometimes reasoning backwards can be much quicker, because say that the computer can adopt any of 100 different starting paths, but the ways to get to the endpoint there are only 2 or 3 ways to get to the endpoint. Well, then in that case, it might be better to start by reasoning backwards from the endpoint, from the solution that you want to, the end state, the goal state, reasoning backwards to, well, if there are only 3 ways of getting to that goal state, then what are the ways of getting 3 prior conditions to the goal state? Then what are 3 ways of getting to those immediately prior conditions? And then what are ways of getting to the conditions immediately prior to the immediately prior conditions? And so that can sometimes make the process much more efficient.